What I want to do is a pretty brief PowerPoint presentation to give you some information on, as well as research data services in the library, which is the group that I'm part of. And then we're going to spend all of the rest of our time in SAS. You have two options in this workshop. You can watch and just kind of follow along if you would like, or you can, if you already have SAS downloaded, you could do the workshop while we're doing it. So it's completely up to you. The code that is on that page that I have up here on the screen is open to anyone. People from other universities, people from working in the government and nonprofits email me questions about SAS all the time from this LibGuide, so you're welcome to use it. So I did mention I want to talk about SAS and department. So to just speak a touch on SAS, SAS is a very widely used statistical software. It is largely used people in demography and health research. And part of that is because SAS is really great at working with big data, and it also keeps a lot of points after the decimal. So you can use SAS to do tons and tons of really detailed research. Somebody was asking if there's a SAS cloud access. You can access SAS online. If you go to their website, they have a good but very watered down version of SAS that you can access. I think it's called SAS Enterprise. So go to SAS or search for SAS Enterprise, and you might be able to use that as well. Okay, so let's talk about research data services a little bit, and then let's get into SAS. I think most people learn SAS best by either doing it themselves or watching someone do it. So rather than me just tell you a ton about it, we're going to work through a bunch of different SAS examples today. This is the first in a two-part series. So what I'm assuming that you know about SAS is nothing or basically nothing. This workshop is really designed towards people who are interested in learning SAS either as a first statistical package or a new statistical package for themselves. The only thing that I assume coming into this workshop is that you have some basic statistical understandings. If you don't, that's fine. Just kind of watch along and ask questions as they come up. So let me talk about research data services a little bit. Services are a group of faculty members and one graduate research assistant housed in the library at Georgia State University. We're called Research Data Services, but we're housed in the Department of Research and Engagement. Our leader is Dr. Swigert Hoa. She is a qualitative data expert, and she teaches series on In Vivo, which is a qualitative data analysis program. And she also teaches some workshops, the first of the series of SPSS workshops, and those are on the website already recorded if you're interested in watching them. Joel Gagowski and Kelsey Jordan are two data visualization people that we have in the department. They teach workshops on Tableau, and Tableau is a partially free. They have a public version, they have a paid version, but they teach the free version of data visualization through Tableau, and it's a two-part series, so it's about 4 hours of training. Joel comes from a business background. He also works closely with nursing and health professions, and Kelsey's background is in the physical sciences. I mentioned this because their really diverse background helps people from a ton of different disciplines with their data visualizations. Then you see myself, I'm Dr. Anderson. I'm a quantitative methodologist. I'm trained as a sociologist, so my background is not in libraries at all. My background is in sociology. I also have a lot of research that's in health, and that's how I know SAS coding. So I've worked with and under several demographers and big health scholars. So a lot of them use quantitative methods, and they use SAS specifically. I also use SAS with the Department of Energy. So I work with the United States government as a statistical consultant, and they use SAS for their research as well. Then we have Jeremy Walker and George Usmanov. They're both in the presentation today. They're here to kind of answer some questions and try to help troubleshoot anything that's going on. So y'all see where, of course, they're also very friendly, as you can see. So Jeremy is the newest faculty member added to our team. He moved to the US, and his background is in data science, and he's really great. If you're interested in learning Python, he's teaching a Python series, and the second Python series is tonight. The first in the Python series is already uploaded. And And then we have George. George, I'm very lucky. I have a phenomenal graduate assistant, and that is George. He's really interested in network analysis, and he's a really phenomenal grad student, and he's working on quantitative methods. So he currently codes in, he teaches a SPSS coding workshop, and he co-teaches with me a 3-part network series analysis, and he does almost all of his analysis in R. So if you have questions about quantitative methodology, please feel free to reach out to one of the 3 of us. I am the only person in the library who uses SAS extensively, so if you have SAS questions, I would suggest emailing me. If you're interested in any general information, that's our website there. I'm going to assume you at least know it somewhat exists because that's how most people find out about our workshops. But check that out. We have a lot of things on there. You know about our workshops at least to some extent because you're in one right now. But we offer over 70 workshops this semester, ranging from data visualization, qualitative methodology, finding data. I taught one this morning on logistic regression, and we teach a ton of workshops on statistical programs. So we cover SAS, SPSS, Stata, and then we also do some methodological workshops on mixed methods, survey design, logistic regression, like I mentioned, and social network analysis. So we have a little bit of everything for everyone. Lastly, if you are a Georgia State or Georgia State affiliate, we have individual and group consultations, and you can email us directly with any research questions you may have. A lot of people have been asking me if I will still meet with people, and the answer is absolutely. We'll just meet in WebEx versus my office or somewhere on campus. So that's Research Data Services, and I introduced George and Jeremy. One of the programs I want to talk about briefly is a data certification. Georgia State Library has a free data certification that you can earn. It's open to everyone, including community members and people at other universities, even people at other countries. It's open to everybody. If you go to 5 different workshops in a single semester, you get the data certificate. It is emailed to you due to we are working remotely right now. It'll be emailed to you in April, and the certificate will have the different workshops that you attended. How we determine who gets the data certificate is who checked into the workshops. So towards the end of the workshop and probably throughout the workshop, a link will be shared for you to check in. Even if you are not doing the data certification, if you could please check in, that way we know how many people came to the workshop, and we like to look at who's coming to the workshop, make sure we're tailoring them to our audience. Talk about is specific to only Georgia State graduate students. GRIP stands for the Graduate Research Intensive Program, and it's a program I started last summer. It's a 2-week intensive, a 70-hour training that's mirrored after things like ICPSR and Stats Camp, only it's more broadly focused on research. So it is a competitive program that graduate students apply to, and they apply through June. They're accepted in July, and the program is in August. This is the only program at Georgia State in the library that we charge for with Research Data Services. It's a $40 fee. Most programs like this run about $1,700, $1,500 to $1,700, and most of them are a week, not 2 weeks. That $40 covers your notebook, printing, jump drives, and most importantly, snacks. We learned last year when we did this that we went through a lot more snacks than we expected. So apparently learning takes a lot of calories. And so that's where the cost is associated. If you're interested in GRIP, please feel free to reach out to me. I'm the director of GRIP, so I'll answer any questions that you may have. So before we jump into SAS, does anybody have any questions about Research Data Services, our workshops, the certificate, or GRIP? If so, please feel free to put them in the chat box. Don't feel like you can't ask questions at any point. The reason that Jeremy and George are here is so that you can ask questions throughout. So please don't feel like you have to wait until a point where I'm like, does anybody have any questions? What I'm going to do is I'm going to focus on the program and focus on the content, and then I will check back in with the chat. And if George or Jeremy want to call my attention to a question that maybe hasn't been addressed, then they'll reach out to me, or it'll be noted. So please just answer questions. I want this to be as close as possible to our face-to-face workshops where people just throw a hand up and ask. So please feel free to type a question in the chat at any time. let me close. And I'm going to pull up the website that I asked y'all to go to earlier. And so this is the site, research.library.gsu.edu/SAS. And there's two tabs here. There's a SAS 1 workshop material and there's a SAS 2 workshop material. On the left, you'll see are the datum points for the workshop that we're going to do today. And on the right, there's a handout. If you are a person who likes to kind of have a physical copy of handouts, you can print this out or you can look at it on your screen, but it's going to cover everything we're doing today. And then immediately below the handout is the code. So this is all of the code that we're going to go over today. And I'm going to just copy and paste that into SAS in a little bit. And then similarly, this is the SAS 1 workshop tab, and then the SAS 2 workshop tab will cover what we cover next week. So just as a reminder, this is the first of a 2-part series. So we'll go from for 2 hours today, and then same time, same place next week, we'll have another workshop that covers more advanced SAS things. So let's go back to the SAS 1 workshop tab, and I'm going to open up SAS. So if you have SAS on your computer, or if you've ever seen SAS, this is what it looks like. Can you do me a favor, because I just want to make sure that nobody is having eye strain issues. Can y'all tell me if you can read this text okay, please? In the chat, please. Okay, so it's readable. Sometimes I go to online workshops and I feel like I have a headache afterwards because it's so small. Okay, so SAS is a little bit confusing until you have data in there and until you have information in there. So I'm going to go to this editor window, which is this bottom editor window. And I'm going to pull the code from the SAS. Pull this code right here. I'm going to start where it is the stars and it says pulling in data and go all the way to the bottom. Then I'm going to paste in the editor window the code. So let me, your screen might freeze because this is a lot of movement, so just give it a second. I'm going to go to the top and then I'm just going to wait just for moments so that your screen can catch up if there's a little bit of a delay. Okay, so looking at this code, you'll notice that there's different colors. There's green, there's dark blue, there's black, there's kind of a purplish light blue, and then you'll see that these lines are all have a highlight function to them. So in SAS, whenever you want to do annotations or put notes into yourself, you simply start the line of code with a star. So anytime that you have a star, SAS will skip that and it will assume that it's just an annotation, it's a note to yourself. Something that's really important about SAS to understand is each line of code, and if you've never coded before, code is what you type into the computer to get statistics to output. So instead of like pointing and clicking into like, you know, file open data, we would just type words in for us to open data. So that's what code is. It's a series of words or commands to run analysis. Each code in SAS ends in a semicolon. So a huge amount of emails I get from people about my code's not working. Can you kind of help me troubleshoot it? A large proportion of them, it's a semicolon that's missing. So every time you have a line of code, it ends in a semicolon. So just so you can see what this looks like, you see how this is green and this is currently dark blue and black. I'm going to remove this semicolon. And do you see how it changes to green? It's because SAS runs until it hits a semicolon. Because this line started with a star, it's going to say everything's in annotation until I hit a semicolon. So I'm going to put the semicolon back in and watch what happens to the code right here. You see how it converts back? So if anything ever seems off, you want to check to see if the semicolon is there first. That's a pretty common error that people have. So in SAS 2, I'm going to show you how to pull in data from other data sources like SPSS, Stata, Excel, R, all of that. But for SAS 1, I'm going to show you how to actually have data in SAS to pull in. So the code to make a database is data. So in SAS, you have to generate a database and then fill that database in. So how to generate a database, the code is data. So this line is saying, make a database and call it SAS1. The reason it's called SAS1 is this is the SAS1 workshop. You could call it whatever you wanted. Like if it was the general social survey, maybe you would call it GSS. Or if it was the census, you would call it, if it was census data, you could call it census. But I'm calling it SAS1 because this is the SAS1 workshop. So I'm going to highlight a line of code. And if I wanted to run this code, and running person at the top, and you can click on it, and that'll run the code you have highlighted. As a general rule, when making a database, it usually works better if you run all the code to generate the database at once. So before we get too much more into this, I want to let you know that some of the most complex code we're doing today is setting up the database. So don't let this overwhelm you. Just kind of understand that it's going to be a little bumpy at the beginning, and then it'll be a lot easier later. Okay, so data defines the database, and we're calling it SAS1. And then we're having this input function. So following input, what do these things look like to y'all? So ignoring the input, but what do these different things look like they might be? Does anybody have an idea? Somebody said subjects. Yeah, similarly, these are our variable names. So we have a variable on age, child, child, class, degree, housing, cat pun, marry, gun, and happy. So these are our variable names. The order of the variable names is exceptionally important. Whatever order you put them in is the order that the database will be made in. Let me say that again. Whatever order you put them in is the order that the database will be made in. So in our database, age will be the first variable, then child, then child, then class, then degree, so on and so forth. So once we have all of our variable names listed, we have a semicolon. So I put the semicolon here so you can see it doesn't matter if it's on the same line, but the semicolon ends the command. So we said, input the variable names, age, child, child, in this order, and then at the end of the variable names, we have a semicolon. So up until we've made a database called SAS1, and we have inputted the variable names that are present right here. Following that, we have data lines. So the data command is going to say, following this command are all of the data points or the data lines. So you see how it's highlighted in yellow? The only time in SAS that it will highlight in yellow like this is when you're in data. Now, I made this database in Excel and I just copied and pasted over. You can also manually type in if you want, but a lot of people just copy and paste it from Excel or a program similar to Excel. So you'll see that there are different lines for data line. So this 47 line right here is respondent 1 or case 1. 6 is respondent 2 or case 2. This 47 here corresponds directly with the first variable in the database, so that's their age. So age is 47. I just knew what variables are, but there's a code book if you're interested in having the code book in the guide that I sent you the link for, the SAS page. And I'll pull it up in just a minute. But this is respondent value for child. So it goes across. This is age, this is child, this is child, this is class, this is degree, housing, capital punishment, marry. And if you scroll, you see that there's 2 more data points for gun and happy. So we have all different data lines for each respondent in our study. And I'm going to scroll to the bottom of that. And you see at the end of the data lines, remember that every single we end a command, it ends with a semicolon. So then we have a semicolon saying this is the end of data lines, and then a run statement. So the run statement is really important in SAS. Run statements are put at the end of blocks of code, and it tells SAS put this whole function together. So it's the closing argument. And you'll notice after the run statement, there's a line that's generated in SAS. Every time that you have the run statement, it will generate a line below it. And this is a really nice visual marker for us when we're coding to see the chunks of code that we have wrote. So I'm going to highlight everything that we've done so far because this is all related to the database. So I'm going to go from the run statement all the way through the data points for our respondents, through the data line command, through the input of the variable names, making the database. And I'm going to hit run or submit. And up here, I'm going to make this screen just a touch. Nope. See what's happening here. So it says, I'm going to run it on the database SAS1, and then I'm going to input this, and then the data lines. And you'll notice that these numbers correspond to the number of run. And then it says SAS went. It said 30 observations and 10 variables. So most people ignore the output, but the output is really important. So 30 observations tells us that there's 30 respondents. And then 10 variables tells us that there's 10 variables. So please always check this when you open up a new or make a new database, because if this said something like 6,000 observations, I would know it uploaded wrong and I need to check my code. Or if it said 3 observations. So I always suggest people check that. Okay, so that was a lot of information, and I want to show you how I annotate code. I do this every time I introduce new code. Immediately following the code, you'll notice that there's a completely common section that explains what that code was. So up above, this said data SAS1. So what you're going to do is compare the old code with this explanation, and whatever is different is what you would replace for your own code. So let me say that again. Whatever is different is what you would replace with your own code. I tried really hard to make the replacements intuitive. So here it says data name. So you would change that to the data name that you want. And then input before said age, child, iChild, so on and so forth. But here it says var1, var2, var3. So you would replace that with variable 1, variable 2, variable 3. And then you see we have all of the different data points and then a run statement. Okay. Do you have any questions about making a database in SAS and uploading it? Okay. So the next thing that I want to do, you'll notice that we didn't get any output of our data. So if you're used to working in R, a lot of times when you open databases in R, it shows you the database. Well, SAS doesn't do that. SAS assumes that unless you ask for it, you don't want it. So SAS assumes unless you ask for it, you don't want it. So we're going to do a way to view the table. And how you view the data in a table is relatively simple. There's different commands that you use. So I always explain commands using words versus just talking about them. So we're going to do a process that's called print. In SAS, anytime you say print, it means show or view. So process a print on the data SAS1. And then I want the observations set to 10. So OBS 10 means show me the first 10 cases. So I'm going to highlight this code and then I'm going to run it. And you'll see now we have a results viewer. Before, we didn't have a results viewer. Can y'all read this? It seems small. How's that? Can you read this? Okay, great. So you see now that it's only put out 10 respondents, but it's made us a pretty decent little table for you to look at. So now we can see, looking at the ages of respondents, the first 10 cases, they range from younger 20s to early 70s. I do want to let you know that I completely missed this data, so please don't take anything away from the data. It's literally just things that I made up in my office one day, but I wanted you to be able to see data points populate. So while I have this up, I'm going to open up that website I told y'all, this handout right here. Just a second. It's mad. Okay. I'll open this up a bit. And y'all will see on this handout, the first page is a code book. So it explains all of the different variables that we're looking at right now. So it says different variables information here. So if you are able to, I would suggest opening this up so it'll help you understand what the variables are as we work through. So we have age, housing, child, cat pun, iChild, married, class, gun, degree, and happy. So these are questions about how old are you? Do you rent or own your home? Do you have, how many living children do you have? Do you favor or oppose the death penalty? What's your ideal number of children? Do you think marijuana should be legal or illegal? What's your social class? Do you favor or oppose gun control? What's your highest degree and how happy are you? If you would like, if you do that copy of your screen by hitting print screen, you would have a copy of this and you can just keep it for the workshop because I'm going to reference it a good bit back and forth when we're doing different stuff. So I'm just going to move this to my other screen and I'll pull it back over when we need it. Okay, so this is our SAS output. Going back to our editor, the difference between this code is OBS 10 and OBS 30. So if this showed us 10 cases, this will show us 30 cases. So we can do process a print on the data SAS1 and show us the observations up to 30. And then I'm going to highlight this and run it. And you'll see that it gives us output of 30 cases. The reason that I show you that with the OBS function, the observation function, is so that you don't try to look at all of your data at once. For a database like this, it's fine because we only have 30 cases. But remember that SAS is made for public health scholars and demographers. And public health scholars and demographers overwhelmingly have giant databases. So you don't want to look at millions of cases or even thousands of cases. You might want to limit it to just a certain number. So in our editor, I'm going to go back to this. If I remove the OBS statement and I just have this code, it will show all of the data. I only have 30 cases, so it's not going to be a whole lot. But if you just remove the OBS statement, it'll show you all of your data there. And then you'll see the explanation of the data in a table. It's easier than the code for making a database. A print for the data, and it's a SAS1 and data name. But because SAS1 and data name are not the same, that's what you would change. So you would change the data name to SAS1. And then there's OBS 30 and OBS with a number. So you would replace that with whatever number you wanted to show. This is very similar to the head function or the header function in R and Python. So you can see the beginning of the data and just kind of check it. So the reason I show you all this is for two reasons. I want you to know how to look at data, but I also want you to make sure that whenever you upload data, you check it, because it's very easy to see errors when the data is up. Usually, if there's huge chunks of data missing, you know that something is wrong. Okay, so I'm going to go back to our editor and I'm going to run how to do frequency tables. So frequency tables are a really common statistical table. They're really basic. And how we run these in SAS, we say process a frequency on the data SAS1. So we're going to do a process just like before we did a process of proc print. Now we're doing proc freq, which means process a frequency on the data SAS1. And then make a table for the variable age. I'm going to highlight this and run it. And you'll see it gives us a frequency distribution of the variable age. So we see all of these different responses that people have. So people range from 22 years old all the way down to 86 years old. And then we have 4 different columns to look at. The first column is kind of obvious. It's how old are people. So these are different ages. The next column is the frequency, and this counts how many people selected that option. So we have one person who's 22. We have 2 people that are 23. We have one person 25, so on and so forth. So the frequency is a count of how many people selected that option. The next column is percent. That's the percent of people that fall in that category. So 6.67% of people are 23 years old. Then we have the cumulative frequency, and the cumulative frequency is everybody on that row and all the rows above it. So you'll notice that this is 3 right here. So if we go and we just trace over to the frequency column, 2 plus 1 is 3. So 3 people are 23 or younger. That's what this 3 means. And then this 10% is saying what percent of people are in those 2 categories. So we're kind of looking at that column or that row and all rows above it. This is really helpful if you want to group your variable. Maybe you want to divide it into thirds or fourths. So right here, 33.3%, you easily group these people and they would be the youngest third of your database. And then you could go down to the 66.67, and then 61 and older are the oldest third of your database. So these different columns are nice. I do want to mention a lot of people learn SAS as a second language, maybe not a first language for programming. There's nothing wrong with learning it first, but a lot of people learn it second. You'll notice that the columns given in the frequency tables are different in SAS than they are in Stata or R. So that's just something to note if you're working between programs, or if you work in one program and your colleague works in another program, that you may have slightly different columns, but that doesn't mean the data is wrong. It just means that the programs present different factors. So I'm going to go back to my editor window, and I'm going to repeat this process with child. So my study might be on how old someone is and their number of children. So we're going to process a frequency on the data SAS1, run a table on the variable child, and run it. So it's the same code as before, only we're adding child in right here. I'm going to highlight this and run it. And you'll see now, instead of having a huge amount of options, we only have 3. So people identified having 1 child, 2 children, or 3 children. And we see that half of people have 1 child. So 15 people, or 50%, have 1 child. And we see that 96% of people have 2 children or 1 child. So 2 kids less. And then lastly, down here, we see that there's 1 person who has 3 kids, which is 3.33%. And the cumulative frequency and the cumulative percent are the total of the number of people in the database and the total percent, so 100%. Now, I'm sure at least one of you has noticed that there's no missing data, that everybody seems to have answered every question. That's because when I made up this database, I didn't have any missing data put in. But in SAS2, I intentionally build in missing data so we can talk about how that works a little bit different. But for this workshop, everything is going to have complete data. So if you find yourself wondering about the missing data, it's because we don't have any. And if you don't know what missing data are points where maybe only 20 people answer the question about child, or some people weren't asked the question about their number of children. So we don't have data points for each person on each variable. Okay, so I'm going to go back to our editor window. And then I'm going to run this on iChild. So process a frequency on the data SAS1. Run a table on iChild and then run it. Now you see this is people's ideal number of children from our data, from our code book that we looked at earlier. So people say their ideal number of children ranges from 0 children to 8 children. So we know that everybody has at least one child from our previous response. So that means that there's at least 4, well, not at least, there's 4 people who have kids that say their ideal number of children is not having kids. So the reason I show you this is for 2 reasons. I want you to be able to look at variables and kind of see how they're broken down. But I also want you to start thinking about, is there some weird kind of inconsistencies through the data or things that might be worth looking at? This is something you should always think about in the back of your mind in relation to outputs. So we have now run 3 frequency tables with this format. Whenever I teach this workshop, I always get this question. Okay, but can I run them all at one time? So look at this code. What do you think we could change if we wanted to run in one set of code, age, child, and iChild? What would I change about this code? Does anybody have any ideas about what we might change here? Feel free to put it in the chat. Any ideas about how we could change this code right here to show age, child, and iChild? What does joint mean? Oh, like add them in together? We can. That's exactly what we're going to do. So here's the code if you want to run multiples at one time. We're saying process frequency on the data SAS1, and then make tables for age, child, and iChild. So these 3 lines of code right here are equivalent to the 9 preceding lines of code that we did, that were each of these individually. Now, I want you to note that the order in which you put the tables in is the order in which they will be produced. So the tables will come out age, then child, then iChild. So if we would have made this in a different order, they'd be produced in that order. But the order in which you put is the order in which they will be produced. So I'm going to highlight this and run it. And you'll see we have age right here, followed by child, followed by iChild. So I want to scroll up just a little bit because I want you to notice something. You see how there's lines in between those frequency distributions? So there's these lines right here. But down here, between the frequency distributions, there's not lines. Remember, in the code, whenever you have a run statement, it puts a line across it, across the code. So let's pull it up. You see this line right here that appears. Something that's really important to note, that whenever you go to print this out, either literally print it or pull it as a PDF, anywhere that this line exists will be a page break. So if you need frequency distributions on individual pages of an output, you would run the frequency distribution separately. But if it's okay for multiple frequency distributions to be on the same page, then you can run it all as one statement. But this is a really important thing that people usually learn later on in SAS, and they wish they would have known it earlier on. So every time you put a run statement in the results viewer, it makes it a new page whenever you export it to Word or PDF. Okay. So that is how to run frequency tables. Does it have questions about how to run frequency tables in SAS? If the answer is no, could you put no? Okay, thank you, one person did. I just sometimes don't know if my computer froze or if people can't hear me. Okay, cool. So nobody has any questions. If a question comes up, feel free to ask it in the chat and we'll get to it either immediately or in a little bit. The next thing that I want to show y'all is how to run descriptive statistics. So if you want to run descriptive statistics on all of the variables in a database, it's a proc means function. That's pretty simple. So it's process a mean on the data SAS1 and run. So you'll notice that there's no identifier for a specific variable here. It's just process the means. If you are not trained by like an old school statistician, all descriptive statistics fall under the category of means. So they're all considered averages or descriptors, which is why it's called proc means in SAS. So that was like an old name for descriptive statistics. So process and means on the data SAS1 and run. So I'm going to highlight this and run it. And you'll see that it produces a table for us that includes the following variables or following information. We have a column on variables. We have a column that's titled N. Now you'll notice that all of our N's are 30 here, and that's because we have complete data. If we had missing data points, some of these may say 29 or 15 or something, but because they all say 30, we know that we have complete data. So this is a nice way to check to see how much missing data you have. Followed by your mean. Your mean is your mathematical average. So the average age of people in this database is 50 years old. And the next column is standard deviation. Standard deviation is a measure of dispersion. So it tells you, is your data heterogeneous or homogeneous? So does it vary a lot, or is it really, really constant? The bigger the standard deviation, the more variance that exists in that variable. So the more the variable has different values for different respondents. Then we have our minimum and we have our maximum. So something important to note here is the minimum is the lowest value someone selected, and the maximum is the highest value someone selected. Not that they could have had what they selected. So this study, this hypothetical study, let's say that it was open to people who were adults. Well, nobody 18, 19, 20, or 21 took the survey. That's why the minimum says 22, and it doesn't say 18. So it's the lowest value someone selected and the highest value someone selected. Now, this is where most people notice that there are so many decimal points here. There's a lot of decimal points that are reported by SAS, and this is because SAS is largely used by public health scholars and demographers, and public health scholars often need tons of decimal points. So most statistical packages hold a large number of decimal points, but SAS reports a high level to give out much more detailed levels of data. So I just wanted to point that out because most statistical software stop at 2 or 3 decimal points, and SAS gives 7, 6 or 7 on most things. Okay. Is there any questions about any of these descriptive statistics that we have here? So a question came in that says, if there are 2 different tables, can we do an SQL database, or how can we analyze them? Is it possible to do that in SAS? So when you say 2 different tables, do you mean 2 different databases, or do you mean like a cross tabulation, combining 2 different tables? Okay, so in SAS, you can have multiple databases open. You can run analysis, have a connector between them. So you need, if you have, say, 2 databases and one is time 1 and one is time 2, you can link them as long as you have an identifier that marks between them. So the identifier respondent ID number, and what you'll do is you'll open up both databases. You'll actually merge them and then run your analysis. But seamlessly through multiple databases is going to be more of a strength of R and Python than in SQL than it is in like SAS or SPSS or Stata. Sure. Okay, so I'm going to go back to my editor window. You'll see the description is right here. So proc, means, data, and then here it's different, SAS1 and data name, so you can replace that with your data name. Now, if you want to run your descriptive statistics by a specific categorical variable, you can do this with a classification argument. So you can process the means on the data SAS1 and then classify it by capital punishment. What this classify function will do is it'll say, now run all of those descriptive statistics by the different levels of capital punishment. So run all of the descriptive statistics by the classifications of capital punishment. So I'm going to highlight this, run it, and you'll see now we have sections. We have this top section where cap pun is 1, this bottom section where cap pun is 2. This is something that's really great about SAS, and something that draws people to SAS is the ability to split variables like this very easily. So of the people who are 1 on capital punishment, and pause just for a second, I want to pull this over so you can see. So if somebody is a 1 on capital punishment, that means they favor, and if they're a 2, they oppose. So a 1 is favor, a 2 is oppose. So here are the people who favor the death penalty, and the people down here are the people who oppose the death penalty. So now looking at this, you'll see that there's different means and standard deviations for age in each one. And this is a nice thing whenever I'm starting to do analysis, I can look at this and see if it looks like there's big differences between the two groups. So looking at these variables and their values, and these variables and their values, you would compare them and say, the age average is 58 and the age average here is 43. So take just a minute and do these and see if anything stands out to you as those might be different between the groups. Just eyeballing it, not testing it statistically. Is there anything that looks like it may be different based on people's views of capital punishment? If you see something that might be different, type it in the chat. And if you think there's nothing that's different, type nothing in the chat. Like not like literally type the word nothing in there. We can see what people think might be different between the two groups. So look at the different means and maybe even the standard deviations and see if you think there might be a difference in these variables between cap pun 1 and cap pun 2. And if you think that they're all the same, just type nothing or no differences into the chat window. We'll just see what people come up with. Somebody last night told me that whenever I stop talking, they think the computer crashed. So I'm just going to kind of talk in the background, but you can ignore me largely so that you don't think the computer. All right, so does anybody see any differences? Even one difference that may exist? So the standard deviations are a bit different between the two groups. Do you see any specific variable that seems like it might be different? One person said age. Did anybody else see a variable or think that age is different or see another variable that they think might be different? So ages come up twice. Is anybody else thinking age or not age? Okay, so iChild, the differences of, so let's look at age and iChild since they both got brought up. So the average age is 58 and 43. That's a pretty big difference. I mean, you're talking 15 years. So that's something to really think about. And then iChild is 2.5 and 3.31. So people who, it looks just kind of eyeballing it, not testing it, that people who are 1 on cap pun, which means they favor capital punishment, may be a little bit older, and they may say that they have a lower ideal number of children. And then someone also may agree. So the degree difference is a 3 versus a 2. So people who favor the death penalty may have higher levels of education, and they may be older. So this is something that we're going to look at a little bit later. Age is the one that really jumps out to me. I mean, you're talking about 15 years. That's quite a big difference. So later on, we're going to do in the plotting, we're going to look at these a little bit. But this is a nice thing to kind of start as a baseline. So if you're interested in looking at an outcome, so if somebody develops a comorbidity or if somebody immigrates or if somebody graduates college or anything like that, you might want to break down the variables by the different categories, and then you might be able to see some patterns emerge. So this is a nice way to get to know your data a little bit better. Okay, so I'm going to go back to our editor. And if you wanted to classify by something else, you could. You would just change this. So I'm just going to change this to child. So you can see the how it looks different with a different variable. The reason I suggest that you do this with a categorical variable, and that's why it's in the code, is because these get really big really fast. So we have 1 child, 2 children, and then 3 children. Now you'll notice here that there is no standard deviation, and that's because you can't have a standard deviation of 1. So a standard deviation requires that there's multiple variables. So blanks don't mean it's broken necessarily. It can also mean that that statistic is no longer applicable. So this is a breakdown of by child. Going back to our editor window, you'll see that we have the information, the code, and the descriptors right below it. So the difference between these 2 sets of code is SAS1 versus data name, and the classifying variable versus variable 1. So you would replace the data name and then whatever variable you wanted to classify it by. So I always build this in as a, like, if we have time, based on how fast the workshop is going. So this is actually code that I have made greened out, but because we have time to cover it, I'm going to run it. So I'm just going to remove these stars. Because a lot of times in the workshops, there's a lot of questions on the front end about uploading data. So sometimes I do this, but since we have time, I want to make sure we cover it. So if you want to run all of the univariate statistics in SAS, this is the code for it. So process a univariate statistic, all the univariate statistics on the data SAS1, and then run it on the variable age, and then run. The reason that I picked age here is a lot of univariate statistics require that you have a continuous variable for analysis. So that's why age is here. And that's also why it says, looking at it, that it's continuous. But you can run this on categorical variables. Just be cautious of your interpretations, because if a statistic doesn't apply to a categorical variable, SAS will still report it. So SAS reports everything you ask for. So it will run things that you shouldn't run on a categorical variable. Okay, so let me highlight this for you. Run it. And you're going to notice that we're going to have a lot of output here. So stick with me. The top section is going to be looking at the general distribution of the data. So you're going to have the N, that's the total number of valid cases. The mean, which is the mathematical average. Deviation, which is a measure of heterogeneity and homogeneity. The bigger the standard deviation, the more that the variable has varying responses. We have skewness. Skewness is going to measure, is the variable skewed to the left or the right in a bell-shaped curve. So we want the skewness to be under a certain value. We have an uncorrected sum of squares. We have our coefficient of variation. Then on the right side, we have the sum of the weights. So if you have weighted data, the sum of the weights will be different than the N. But if you have unweighted data, like what we have here, the sum of the weights will be equal to the N. Then you have a sum of the observations. So what this does is it adds up every single person's value on age. Because remember, this is all for age. So we have 1,525, which means everybody in the database, if we added them up, this is how old they would be collectively. On a variable like age, this doesn't really tell us a whole lot, but imagine that you are somebody who is interested in studying years of experience, and you wanted to say, how many years of experience do people have across the entire corporation? This is a nice way to get that information. Then we have our variance. And variance is just the squared of the standard deviation. That's why it's on the same line. We have our kurtosis. Kurtosis measures the peak or the flatness of our distribution. Skewness and kurtosis are usually used in concert with each other to talk about distribution of the data. So you would want both of them to be under a certain threshold. We have the uncorrected sum of squares next to the corrected sum of squares. And we have our coefficient of variation with our standard error of the mean. The reason that the corrected sum of squares, uncorrected sum of squares, coefficient of variation, and standard error of the mean are all produced in the univariate statistics is because SAS is largely used. I know I've said this like 5 times, and I'm probably going to say it 5 times more. It's used by health scholars, and it's used by a lot of demographers and economists. And a lot of those groups use these values specifically, so it's a default. The next section is basic statistical measures. On the left, they call them location. They are your measures of central tendency, which are your mean, your median, and your mode. Remember, the mean is the mathematical average. The median is the 50th percentile, so you break the top half of the data from the bottom half of the data. And then the mode is the most common response that people give. So the mean is the average age, the median is the 50th percentile, and the mode is the most common age. On the right, under the column header of variability, are your measures of variability. You have your standard deviation and your variance. You'll notice that these are repeated values from up here. But they give them broken down in different tables, so if you want to rip just the basic statistical measures, then you only have to look at one thing. You have your range and you have your interquartile range. Something that I want to note, if you're a person who uses other stats packages, is SAS gives you the literal range, not the minimum and maximum value. So it actually calculates the range for you. And the same for the interquartile range. So the middle 50% is the interquartile range, and it gives you the values for that. So that's what those top 2 are. And then we see the test for location. So these are going to be your t-test, and they look at kind of the distribution of the data. So you have your student's t, your sign rank, as well as the associated p-values with each of those tests. So we see that the t and the sign rank are all statistically significant because they're less than 0.001. This is largely unused by researchers, but this is testing mu naught, the kind of null hypothesis of the distribution. Then we have our quantiles. So this gives you tons and tons of percentiles in here. So it starts with the highest value, and then it breaks it down 99, 95, and 90. Then it follows with 75th, which is your third quartile, which is why it's called Q3. Your 50th percentile, which is the median, and the 25th percentile, which is Q1, followed by 10, 5, and 1. You'll notice that these mirror each other. So 0 and 100, 99 and 1, 95 and 5, 90 and 10. The reason that these exist is so if you want to remove outliers. So outliers are going to be extreme values. So if you are in a discipline that removes the 1% outliers, you now have those values. Or if you remove 5% of outliers or 10% of outliers, you know where those values are. And then lastly, we have extreme observations. So this is going to tell us the lowest values and then what observation number they are. So this person is 22 years old and their observation 28. This person is 20 years old and their observation 23. This person's also 23 and their observation 8. So the value is going to be the value that people have in the database, and OBS is going to be the line or the number respondent they are. The same is true for highest. So person 29 is 74 years old. Person 30 is 75 years old. The purpose of this extreme observations is so you can easily identify the outliers. Yeah, exactly. So these are extreme observations are synonymous with outliers. I know that was a lot of statistics. Does anybody have any questions about any of these in the univariate function? Okay. Let's go back to our editor. And so this is just rerunning those tables. So we're going to skip that. We've already done it. Now, the next thing I want to show y'all is how to run cross tabulations. So a frequency distribution is a distribution of a single variable. A cross tabulation is overlaying two of those frequency distributions for two variables. So here we're saying we want to process a frequency. Now you've seen frequency before with the tables function when we did frequency distributions. Frequency distributions and cross tabulations are very similar. It's just a cross tabulation is an overlay of two frequency distributions. So we're going to process a frequency on the data SAS1. We're going to run a table on Mary. This little star makes it a crosstab by gun. So we're going to look at Mary by gun. I'm going to pull over our code book again so we can look at what does Mary and gun values mean. So marijuana, do you think marijuana should be legal or illegal? So 1 is legal, 2 is illegal. And we're going to run that by gun. And do you favor or oppose gun control by the government? 1 is favor, 2 is oppose. So for Mary, 1 is legal, 2 is illegal. I'll write that down. 1 legal, 2 illegal. And then 1 is favor and 2 is oppose, and this is gun control. Right. So I'm just going to pull this over for us. All right, so I'm going to run all of this code together. And just to say it again, it's a process of frequency on the data SAS1. Make a table of Mary by gun and run. Came in that says, do the variables need to have certain characteristics to run the cross tabulation? For example, do they both need to be continuous? You can technically make a cross tabulation on two giant continuous variables. It just makes them really hard to read. Most people do cross tabulations on categorical variables. So variables like what we have, like legal, not legal, favor, and oppose. But there's technically not a right or wrong for size of variable for a crosstab. It's just if you make them really big, they're almost impossible to read. Okay, so I'm going to run this. And we see that we have a little baby table that's produced. So this is gun, and the 1s are the people who favor the death penalty, and the 2s are people who oppose the death penalty. I'm sorry, this is gun control. So for gun, this 1 is people who favor gun control, and 2 is people who oppose gun control. And then we have Mary, and that's the marijuana question. So people who have a 1, these first group, think that marijuana should be legal, and people who are in the second group think that marijuana should be illegal. So the first value right here is the frequency. So that's how many people say 1 on gun and 1 on Mary. So this cell right here is people who favor gun control, and they think that marijuana should be legal. So there's 13 people who favor gun control and think that marijuana should be legal. These people right here, there's 6 people who say they oppose gun control and they think that marijuana should be legal. And then following this, this is what the cell goes in order. The first is the frequency. The second is the overall percent. So of all the different cells in the cross tabulation, what percent of them are in this cell? The third one is the row percent. So everybody in this row, how many of them fall into this cell? And then the fourth one is the column percent. And that's everybody in this column right here. How many of them are in the cell? Now, I didn't memorize that. I just have this little legend right here. So the first number is frequency, then percent, then row percent, lastly column percent. So the one that you interpret is based on what you need. So if you want to talk about how many people are in a cell, you would use the frequency. If you want to talk about what percent of people fall into a category, you would just do percent. This is overall. And if you want to talk about a specific row, so people who think that marijuana should be legal, you would use the row percent. So of the people that think marijuana should be legal, 68.42% favor gun control. And of the people who think that marijuana should be legal, 31.58% think that they oppose gun control. So you can interpret across rows. You can also interpret the columns. So let's interpret for gun 2, which is oppose. So of the people who oppose gun control, 75% think that marijuana should. And of the people who oppose gun control, 25% think that marijuana should be illegal. So that explains all of the values in these specific cells. Now, as far as the row totals go, it reports the frequency, and then it reports the column percent. So in the row total, it reports the frequency and the column percent. And then in the bottom of the columns, it reports the frequency and the row percent. So 22 people favor favor gun control, which is 73.3% of all of the people in the study. So looking at this, some people often get confused and they're like, that's just too many numbers in that cell. I want to pare that back. So I want to show you all how to do that. What you can do is you can use these no statements. So this is the same code as before, but it has this section right here. So process a frequency on the data SAS1. Make a table for Mary by gun, which is what we did before. And then there's a slash, and this is a after statement. So I want you to also make no row, no call, no freak. So no row means I don't want row percents. No call means I don't want column percents. And no freak means I don't want frequencies. So if I take out row percents and column percents and frequencies, what will be left in the cell? If I take out row percent and column percent and frequencies, what would be left in that cell? Does anybody have a guess? No, because remember, freak is the actual number. Taking out the row percent, the column percent, and the frequency. So what this will leave is the overall percent. Yeah, exactly. It'll leave the percent. So I'm going to run this code. And you'll see now in this little baby cell, it just has percent. And then that just reports the percents for you. The reason I want to show you this is multifaceted. One, so you know about the backslash option so you can remove things. The other reason is because if you're a researcher and you're trying to share your research with other people who may not be really statistically savvy, don't give them more information than what they need. Because if I walked into a room of non-stats folks and I gave them this, some people would immediately just kind of shut down because that's a lot of numbers and it's hard to understand what they are. But if I walk in and I give them this and I say, the number in the cell is the percent of people in that cell, then people understand that very easily. So you want to always think about your audience and think about who the information is for. Very little of our research is for us. Almost all of it is to share and disseminate. So you want to make sure that the way you make it is really effective. So I'm going to the editor window, and I'm going to give you a thing to try to practice on your end. I want you to rewrite this line of code, and I'm going to copy it and paste it into the chat. And what I want you to do is rewrite that line of code so that I have column percents and frequencies. So I want column percents and frequencies. So what would I change that code to? So I would have column percents and frequencies. So trying to rewrite that code. I know it's not the same as like sitting in a workshop, but this is me trying. So make it so that it has column percents and frequencies. How would you write that? Okay, does anybody else have code or agree or disagree with what we have? So I'm going to copy that and paste it in, and we're going to see if it gives us what we need, okay? So we want column percents and frequencies. So here we have frequencies in percents. So how would we edit this code? It's close, but we don't need percents, we need column percents. So I'm going to try this other code that was put in. Look. I'll get to your question in just a second. So I'm going to add the semicolon on. And you see that it's blued out. So what this is, it's very close. You want to type percent. So PER will not hack it. You have to have percent. So let's run this and see what happens. So we wanted frequencies and column percents, and that's what we have here. So nice job. It worked. Just make sure that you have percent wrote out. Here's a question that came in that says, this is a 2x2 table. So does SAS have formulas to calculate the measure of disease occurrence and measures of association? Yeah, you can do measures of association like lambda and gamma. You would just have to add those on separately. So do me a giant, will you email me and I can work through that code with you? That's not something that people use a whole lot, but I'm more than willing to work with you on that. So just send me an email. And George, can you post my email address in there for them to grab, please? Okay, so nice job, this code. Do y'all have any questions about the cross tabulations? So here is some code that's a little bit broken. So you notice that there's a lot of purple that flies through. So here's my question for you. I want you to take a second and try to figure out what you think is wrong with this code. I will tell you there is a piece of punctuation missing, but kind of look at the code and see what you think might be wrong here. Okay, so we have a missing quote. Where would that quote go? You're absolutely right. It's a missing tick mark. Where would it go? Do you have any ideas? After children. Perfect. So I'm going to add this tick mark in. And do you see how everything shifted for us? So I'm going to take it out, and you see all of this is purple. And it stops right after the tick mark. So the reason that I build this into the workshop is so that you know what it's like to see code that is obviously wrong. Like we haven't had anything with that much purple. And if you go to at the end where it converts back, you usually can find where the error was. So I put this tick mark in after children, like we suggested, and you'll see that it fixes it up for us. The reason that it was all purple is because in SAS, when you put a title in, it says, okay, that title is applicable until I hear or until I see another tick mark. It's like an annotation. So it's waiting for that tick mark for it to say this is the end of it. So we're making a bar chart here. And it's saying title of the bar chart for ideal number of children. And then process a graphical chart on the data SAS1. And then you have to identify what kind of graphical chart. So you're going to run a VBAR, which is a bar chart, on the variable iChild, and we want to make it discrete. I'll rerun this without discrete later, but we're going to keep the discrete function in for now. And what discrete does is says, whatever categories already exist, those are the bars I want you to generate. And I'll show you this, and then our run statement. Okay, so we see it says bar chart for ideal number of children. And then do you see how there's a individual bar for every single response option that we had? So people could say 0, 1, 2, 3, 4, 5, 6, 7, 8, and 8 is 8 or more. Or no, 8 is 8. Why do you think 1 doesn't exist? So 1 as a column isn't here. Does anybody have an idea of why 1 may not exist in this bar chart? So there's not a 1. So somebody said there's not data for it. It's because nobody said their ideal number of children was 1 child. Exactly. So SAS reports what it has, not what it could have. So somebody could have said 1, but nobody did. Therefore, there's not a bar for it. This is a really important thing to note because other statistical programs would put a blank in there. And so if you're looking at bar charts that are created in SAS versus other programs, sometimes people get a little worried thinking that their data is broken because they see that there's a column right here when in other databases, there's a blank. So that's just something to note. It's just because they don't report something that you don't have. Okay. So I mentioned earlier that this was using the discrete function. The discrete function breaks you down by each column that exists. So I'm going to go back to the editor window, and I'm going to remove the discrete option. I'm going to backspace it out, and then I'm going to rerun this. And you'll see now that it puts in midpoints. So 0, 2, 4, 6, 8. So I'm just going to scroll up so you can see the other ones kind of side by side. Y'all see how this is 0, 2, 3, 4, 5, 6, 7, 8? And then down here, it collapses them. So in SAS, if you don't tell it to do discrete, it will collapse them into categories and then make a bar chart out of it. So for most of us, if we're using more continuous variables or really variables that range a lot, you can use the midpoint. But you want to identify the different categories if that's important. So there's, what is the frequency on the y-axis depict? It's the number of people who said that category. But down here, this is the midpoint. So this is collapsing these groups into these categories. So this is saying people who are 0 through, I think, 0.75 or so, and then people who are 0.75 to about a little shy than 3. And so it just collapses them on the midpoints right here. You should not do this with things like number of children because you have now technically collapsed people without kids and people with kids together. So you want to be careful about this. As a general rule, I always use the discrete function. So you would just do the slash and then discrete in here. And that'll allow you to identify each individual category. So I'm going to swap this out for iChild and make it age so that you can see this again. So see how this looks kind of wonky because you have so many ages and categories? I could go in and then remove the discrete function and rerun this. And then it collapses it down and identifies the midpoint. So it really matters on what you're doing. If you're doing something like age, I think it matters less. But if it's something where it's distinctly different between something like how many degrees do you have? Like having no degrees is very different than having 1 degree. Having no children is very different than having 1 child. But there's other factors that it doesn't really matter. If you are okay with the midpoint, just don't use the discrete function. But the discrete function says each category of this variable I want to be its own bar. So do you have any questions about bar charts before we move into some more statistics? I want to show y'all start doing some like heavier hitting statistics. We're still not going to do anything like life-changing, but I want to show you like some correlations and things like that. So we're going to run a correlation first. This is saying process a correlation on the data SAS1 and then use the variables iChild, child, and age. So we're going to look at the correlation of the data of variable iChild and age. So I'm going to highlight this and run it. And what we see here is this descriptor. Oh, I did never take the title off. That's kind of funny. So the title stays until you take it off. So this is the title from our previous graph, but this is the correlation output here. You see that the top box is a reporting of the statistics, a breakdown of each statistic that you asked correlations on. So you have the mean, standard deviation, the sum, just because this is kind of different in SAS, so I want to mention it. Sum is the total sum of that variable. So everybody's ideal number of children added together is 88. And the lowest value and the highest value. Same for child and age. Then the second table is going to be the correlation coefficient outcomes. So a variable correlated with itself is a perfect 1, so it just reports the 1. You'll see the axis is a 1. And then if you want to look at the relationship between iChild and child, it's right here. So the top number is the correlation coefficient, and the second number is the probability. So this is a really weak positive correlation that is not statistically significant. So just as a reminder, your p-value has to be less than 0.05 in almost all disciplines to be considered statistically significant. And this is well above 0.05. So there's not a significant correlation between children and actual number of children. I am 99% certain that this would exist in real data. Just remember, I made this up, so that's part of it. Then we see for iChild and age, the correlation is 0.38, and it is statistically significant because it's less than 0.05. So with my made up data, there is a positive, moderate correlation between ideal number of children and age. The reason I say positive is because the number is positive, and the reason I say moderate is because it's between 0.3 and 0.6. Below 0.3 is weak, above 0.6 is strong. So this is a moderate positive association between iChild and age. As people get older, their ideal number of children increases. Now you will notice that these mirror each other. So 0.03278, 0.03278. That's because this is iChild with child, and this is iChild with child. So this correlation coefficient matrix in some programs doesn't report the top half. It only reports the bottom because the numbers are the same. So don't let the fact that there are double as many numbers make you think something's wrong. It just means it's reporting above and below that. And then the last one to interpret is this age and child. And we see that it is not statistically significant because it's above 0.05. But if it was statistically significant, it would be a negative weak relationship, which means as one thing increases, the other decreases. So this would be saying, as somebody got older, their number of children decreased. So that's what that relationship is there. So this is the correlation coefficient output. It's pretty simple. I really like these simple statistics that are produced at the top because it allows you to look at the distribution of the variables that you're examining, not just the correlation coefficient. Does anybody have any questions about the correlation procedure? Oh, there's a question about how do you combine more than two variables in a bar chart? It's called a stacked function. So you do a stack, and what you can do is you can actually stack variables on top of each other. And you can also do a group. So stack does a stacked bar chart, and then grouping splits the bar chart into multiple groups. So let's say that you wanted to run your ideal number of children by men and women. You could do, if you wanted men on the left and women on the right, that's called a split. And if you want to put men's ideal number of children on the bottom and women's ideal number of children on the top, that would be called a stacked. So it's a stack and split function. And that code I can email to you as well. Or it'll be up on website. Jeremy, George, and I are working on updating our websites about statistical packages, and that's actually a exact code that we walk through on that. So it'll be up soon, but if you want it more than, I don't know, in the relatively near future, I don't want to give a date, email me and I'll send it to you. I have the code already. Okay. Questions about correlations. Remember, you should run correlations on continuous numerical variables, so variables where the responses are numbers and the numbers mean something. They're not assigned to another variable. So you shouldn't really run a correlation on something like people's country of origin and their favorite color, because those aren't continuous variables. So you want to run correlations on continuous variables. All right, so I'm going to go back into the editor window. That's our correlations, and you see the descriptors right below it, just like always. Process, a correlation on the data, and this says data name. So these are different, so you would replace that from SAS1 to the data name. And then var, child age, var, variable 1, variable 2, variable 3, so you can put them in. Of note, you can make a correlation matrix of 100 variables or 2 variables. You have to have at least 2, but there's not an upper limit. They just get really unwieldy after a certain point. So I usually try not to make them bigger than 20 by 20, but you can do whatever you want. Okay, so the next thing that I want to run is a regression. So we touch correlations. Correlations tell you if 2 variables are related to each other. Regression allows you to predict an outcome variable. So the code for this is process a regression on the data SAS1, and then you use the function model. Model says, what do you want to model? And model means predict in SAS. So we want to model the variable iChild. So this is our dependent variable, and make it equal to child, age, housing, and happy. So what this is measuring is use these 4 variables to predict iChild in a regression. So if you haven't used regressions in a while, or if you're kind of new to regression research, it's predicting a line. So if I know someone's number of children, their age, if they own their house, and if they're happy, it's predicting their ideal number of children. So I'm going to highlight all of this and run it. I want you to take a deep breath if you have made it this far and you're still super paying attention. There's a lot here. So just stick with me. So I still haven't taken that title off, so try to ignore that. Sorry about that. We have at the top, you see it's the reg procedure, and it's model 1. So if we ran it would be model 1, model 2, model 3, model 4. And this is a nice thing, so that if you're doing model building, the order in which you run them is the order in which they'll be produced. So it makes it easy to search through your output later. You see that our dependent variable right below this is iChild, so we're predicting ideal number of children. Following that, we have a box that says number of observations read and number of observations used. So these numbers match because we don't have missing data. If we had missing data, those numbers would be different. So number of observations read is the total number of observations in the database. Number of observations used is the total number of observations that were actually run in the model. So SAS by default uses a thing called listwise deletion. And listwise deletion says, if you don't have an answer on every variable in the model, we drop you from the analysis. So if you can change this if you want, but the default is listwise. Listwise is almost everybody's default. I actually don't know anybody who doesn't use listwise as the default. So just to reiterate, the number of observations read is the number of observations in the entire database, and the number of observations used is the number of observations that were able to be used in the analysis. The reason that these numbers are the same is because we don't have missing data. The next section is the analysis of variance. Remember that regressions fall under general linear models, and so do ANOVAs. So we actually use ANOVAs to test our regression. And this will give us our model fit, our error fit, and our corrected total. So the error is going to be the residual, and the model is going to be what we predicted in our model. So we see here that we have pretty huge error terms. Our error term is 93, and what actually fit in the model is 18. So we see that there's a huge amount of error. This is because, again, I made up the data. On the right side, it reports the F statistic, which is your overall model fit for regression, and it gives you your p-value. So this p-value has to be less than 0.05 in most disciplines to be considered statistically significant. But it's not, but we're still going to go through it because I want you to know what the data means. But usually you would stop right here because it's not less than 0.05. The next section is going to be talking about model fit. So you have your root mean squared value. That's MSE, is root mean squared estimation. We have our dependent mean value, our coefficient of variation, our R squared, and our adjusted R squared. Out of this table, this output right here is what most people look at. The adjusted R squared will say how much of the dependent variable is accounted for by the model. So how much of the variance in the dependent variable, or here I child, is accounted for in the model. So it says about 3% because this is a proportion, and you can convert a proportion to a percent by multiplying it by 100. The next section is the parameter estimates. This is where most of us spend all of our time when we run regressions. So this is your estimate or your beta value. Now, something that's different about SAS and other programs is it starts with the intercept. Out of the gate, it says, here's what your intercept is. So this is the predicted value for the parameter. This is the standard error, followed by your t-value and your p-value. So the two things that people look at the most are the p-value. If it's less than 0.05, you know it's statistically significant. And then if it is statistically significant, you interpret the parameter. Now, some of y'all may know this as your coefficient. Most disciplines and programs call this your coefficient, but it's called a parameter estimate in SAS. So looking at these different p-values, we see that they're all really high, and the only one that's approaching statistical significance is this one right here, so 0.06. So we would look at this value, which is the parameter estimate. We see that it's a positive number, and we see that it's a very small number, so it's weak. So we would say that there is a positive weak relationship between respondents' age and their ideal number of children. If the number is negative, like it is for the intercept, that means as one value goes up, the other value decreases. So if it's not, but let's act like child was negative 0.36. That would mean as people's number of children increases, their ideal number of children decreases. So positive means they go in the same direction, and negative means they go in opposite directions. That's a lot of numbers. Does anybody have any questions about the number of observations table, the analysis of variance table, the model fit table, or the parameter estimates table? A lot of things going on here. Okay. The next thing that you're going to see is we have this huge amount of different error fit diagnostics. So most of us never use any of this, but I want to walk through it kind of quickly so you can see the different things that are going on here. Our studio is, wow, my brain is gone. SAS is really about visualizations. So is R, which is why I said that. So SAS is all about visualizations, especially when it comes to fit diagnostics. So fit diagnostics are going to say, using different tests of the error. So not what we predict correctly, but what we predict incorrectly, the fit diagnostics addresses those. So we see that this is the fit diagnostics for the overall residual. And this is using the R student predictor, other R student, well, this is the same R student predictor using predict versus leverage. So these are the two different ways R student is tested. And then if you want to look at the quantiles, remember 0, 25, 50, 75, 100, this is the residual of the quantiles. And this is the predicted value. So if you're doing just straight predicted value, you can see that it ranges kind of from 2 to 4, a little bit more, and it allows you to see the difference here. This is the test. I fully recognize that most of you probably don't use most of these. So if any of these sound familiar, like perk up your ears and pay attention, but a lot of these you probably don't use. This is a Cook's D test for the observation, followed by a distribution of the residuals using a normal distribution to see how they fall. If you want to test the fit mean versus the residual of the proportion less function. And then in the bottom corner, it gives you just general information. So how many people answered this, that's observations. Parameters are the different predictors. The error degrees of freedom, the mean squared estimation, the R squared of the error, and the adjusted R squared of the error. And then lastly, there's another set of tables here that does the residuals by independent variable. So this is the residuals that exist for child when predicting iChild. These are the residuals for age, housing, and happy. Now you'll notice that there's a line that goes across it. So that is talking about, do you over predict or under predict? So 0 means that you hit it right on. Yeah, it's a plot of the residuals. Yeah, for sure. That's a good question. Somebody asked, is this a scatter plot? Yeah, it's a scatter plot of the residuals. So what SAS does is it produces a scatter plot of all the residuals across the different options. Can anybody tell me why for child there's only values at 1, 2, and 3? Does anybody have any idea for this specific child variable, why are there only values at 1, 2, and 3? Any ideas? Yeah, it's a discrete variable. People can't have 1.5 kids. That's why there's not a value here. So let's go to 3. It's the easiest one to see. Do y'all see this is the residual? So this means that you predicted right on would be if it's on the line. So this person with 3, do you see how they're really, really close to that line? That means that they have very, very little residual, which means we either predicted them right or almost right. But over here on 2, we see that some of these have huge residuals. So this person is 4, which means we underpredicted them by 4. So it's not saying how many kids do they have. That's the 2 right here. But it's saying how much did we underpredict them. So this is off by 4. So this person has 2, and they would say that their ideal number of children is 6. So this is just looking at the difference between what we thought their value would be and what their actual value is. When I first learned SAS, I found this very overwhelming, this output, and I found myself largely ignoring it. And the more and more I got into research, I found myself spending a lot of time with these residual regressor tables because they really help you visualize what's going on with your data. I always find these very, very helpful, and I find myself going to SAS just to run regressions so that I can see this output, look at who am I predicting incorrectly. Because let's talk about this child just a little bit longer. If all of the values for 3 were really, really close, and then they were super spread out for 2, I would know that I'm predicting my 3 number of children really well, but I'm poorly predicting my people with 2 number of children. So maybe I need to spend more time looking at this category of people who have 2 kids and see what else I need to include in my model and make sure their data is right. So I find these tables to be really helpful when I'm trying to do things like model fit, or if I have a value that's just outside of significant and I want to see what's going on with that variable's errors. This is a really nice way to look at it and really see what's going on. I know this is very high level and beyond kind of a SAS 1, if you will. But does anybody have any questions about these scatter plots, these graphs for fit diagnostics, or any of the regression information we've talked about? Okay. The last thing that we're going to do is we're going to ANOVA. So the reason that I try to make sure that I always cover ANOVAs and workshops at Georgia State is because there is an astronomical amount of ANOVAs being done across. Right before I got hired for my job talk, I did a bunch of research on research at Georgia State, and I found that over 30% of publications that come out of Georgia State, of the ones that I sampled, used ANOVAs. So I want to make sure that I always cover ANOVAs for the Georgia State scholars and scholars abroad, but I try to just mention that ANOVAs are really widely used, so I think they're super valuable to look at. ANOVAs fall under a classification called general linear models. So we're going to say process a general linear model on the data SAS1. And we want to classify it by gun. And then we want to model age by gun. So gun is going to be the categories that we're using. Now, I want to say this before I run this. ANOVAs require that you have 3 or more groups. This database doesn't have a variable that works really well for this, so I use gun, and I'm just mentioning out of the gate, so if later you're looking at this, technically this should be a t-test, but we're going to run it as an ANOVA, just so you can see it. So just to say the code again, process a general linear model on the data SAS1. Classify it, so this is the grouping variable, by gun, and then model age by gun. I'm going to highlight this and run it. Scroll up. And we're going to see, again, I didn't remember to change the title. So the title carries as long as you have it up there. So this is going to be a general linear model procedure with a dependent variable of age. So it's saying split up, check and see if age is different by these different groups. So this first table is going to talk about your overall model fit. This table should look really familiar. We just had it in our regression. So SAS reports this for all general linear models. So it would be in an ANOVA as well as in a regression. This is going to say the model fit. So how much of the model fits well. So how much does gun predict age? Because remember earlier, we mentioned how age and gun seem related. So this is us testing that. And then our error term is astronomically huge. You always want to compare the model sum of squares to the error sum of squares. And if the model sum of squares is notably smaller, that means that your model probably is not statistically significant. And then this is the corrected total, which is close to the summation of these two values. Then we have our mean squared for our model and our mean squared for the error. This is a model fit measure. On the far right here, we have our F statistics and our p-value. So the F statistic is going to be the calculated F statistic, and the p-value is if the model is statistically significant. The model is not statistically significant because we see that it's greater than 0.05. So we're going to still examine it, but it's not statistically significant. Let me get to your question in just a second. But I see it. I'll make sure I answer it. So here we have our R, which is going to tell us how much of the variation does the grouping account for. And this is a proportion, so 0.001 translated into a percent is 0.1%. So it's really small. This is our coefficient of variation value. This is our root mean squared estimation. And this is our average for age. So it says age mean, it's our average age. So then we can do our grouping, and it gives us our type 1 sum of squares with its mean squared and its F value and our PF. And it also gives us the type 3 sum of squares. So based on which of these you use is what you would report. You're going to notice that for this, they're the same. Based on how many values you have and the variation of those values, these values are not necessarily the same. But these are different type of tests. This is a type 1 sum of squares right here. This is a type 3 sum of squares. So this ANOVA is telling us that these groups are not significantly different from each other. So there's not actually an age difference. And I mentioned earlier how SAS really likes to give you visualization so you can see what is working and what isn't working, and it gives you a nice distribution. So looking down here at the distribution of age, it gives us 2 box plots by groups. So this is for the gun control by age. So gun 1, remember, is favor gun control by the government, and 2 is oppose gun control by the government. So when we look at these 2 variables, we'll see that they overlap quite a bit. Now, this middle box that is on both of these box plots is the middle 50%. And you'll see that we have the line across, and that is our median. The line across is our median. And then this diamond is the mean. This is something that's different about SAS and other packages, is it gives you the mean in your box plots. This is really nice because if you're here, we see that our mean and our median are very close, and that tells us that the data is not heavily skewed. But here we see that our mean and our median are different, which would make me think that this data might be skewed a little bit and not fit into a normal parameter. Just to remind you, for box plots, the top line is the highest value minus outliers. The bottom line is the lowest value minus outliers. And this big box is the middle 50%. So looking at this, you can see that the middle 50%, they largely overlap. And to be statistically significant, these would need to be different than each other. So this box would have to appear almost up here for it to be statistically significantly different. So even though the averages, when we looked at that first table of gun control by all the different descriptive statistics, we thought that there might be something going on with age, but once we actually test it, we realized that it's not. The last thing that I want to really point out on this is in the top of the table of the graph, it reports the F statistics and the probability. This is because, again, SAS is largely made for public health researchers and demographers, and public health researchers almost always report the F statistic and the probability of F, or the p-value, on all of their ANOVAs. These are very standard in those disciplines, so that's why it's produced here. This is why when you talk with people, or let me back up, when I meet people and I find out what programs they code in, they really don't have to tell me a whole lot about their research. I usually can kind of figure out what they do based on which package they use. So if somebody tells me, with a couple of exceptions, but if somebody tells me that they're an SPSS user, I know they're either trained by an older researcher, or they're probably in the early stages of research. And if they do Stata, I know they're probably a social scientist. If they use SAS, I know they're probably doing health research. And if they use R, they could be anything. R is always the wild card, but it's nice to kind of see how the packages are programmed for different people. One of the questions that came in, or a question that came in, was saying, how can we use ANOVA for testing 2 or more variables, like similar to a t-test? Well, remember that ANOVAs and t-tests are distinctly different. So if you want to run an ANOVA, you would just do a different classification here that use 3 or more. So like child would work well because there's 3 groups in child. So you would just edit the code and put in your new classification. But if you want to run a t-test is actually completely separate code. So if you want to run a t-test, just shoot me an email and I'll send you that code. Does that answer your question? While they're typing in their answer, does anybody else have any questions? Okay. Type them in if you come up with them. So just to kind of wrap up a little bit, let me pull up this. Oh, thank you so much. So I think Jeremy posted a bunch of links for you. I'm also having it on the screen, but if you please check in, you want to use bit.ly, and it's in the chat. If you scroll up just a little bit, it's linked to check in for workshop attendance is there. So please check in, even if you're not going to do the certificate, because it allows us to know how many people came, what institutions or communities are you from, and things like that. Between now and SAS 2, if you're interested in coming in SAS 2 at same time, same place next week, please do yourself a favor. And if you can download SAS, which is a lot of y'all are Georgia State, so I know you can, if you'll download the program and then run through the code yourself and come in and let me know if you have any questions. I've learned that the people who get the most out of these workshops spend a little bit of time, usually about an hour between the first workshop and the second workshop, and rerun the code themselves. So please check in, and I will stick around and answer any questions that people have. If you have some SAS questions that like things you want to learn how to do in SAS and it wasn't covered today, please feel free to ask it or send me an email and we can talk about getting you some code or talking through it with each other.